I've got my transistor tester here all built. Right now it's showing emitter base collector. Let me just speed up the clock here so I can lock that in. Alright, it's showing emitter base collector up here for that transistor that's under test right there. And this one here, and it's also telling me down here that it is an NPN type. Okay, now you can see here, this is, I'm just using regular LED displays, 7-segment LEDs. These are common cathodes, common anodes. They're common anodes. And so anyways, I'm going to start up here with the clock. This is just basically a clock. It has the timer right there with an adjustable frequency adjust there. This is a binary counter, 0 to 9, so it's a 10-digit counter. That's displayed by the LEDs here, and then it's converted by the 7447 into a decimal display. Right now it's going really fast, but if I slow it down, it's only counting from 0 to 2. Okay, so that's basically 3 clock pulses. Now, the way this works is these clock pulses are coming in, the binary data is coming into here. This is a 74154 demultiplexer, and the data lines that are coming in here, the binary data that's coming in here from the counter is coming out of these pins on the bottom. And the 4th pin is going back to this resistor transistor here, which sends a pulse back on this yellow wire back to the counter to reset it when it counts to 2. Okay, and the reason I did that is because I wanted to only count to 2, because I only have 3 transistors on the prom, so that would be the 0 position, 1 position, and 2 position, and then it has to start over again from 0 to 2, 0 to 2, and it basically goes around all the time. So I don't need it to count anymore. Now this is active low, and the ROM, it needs active high. So what I did was I sent the output into an inverter, hex inverter, 7404, and then I took the output, and you can see here it goes directly into the ROM card. And so what happens is you see that LED flashing right now. This little circuit down here is one transistor with 3 diodes. This is basically a 3-input NOR gate. And the sum of the NOR gates for the transistor being tested comes out of this wire into the LED and into this black wire here into the 74LS164, which is the serial in parallel out shift register, 4-bit. And I take that output into these wires that goes into this logic circuit. Okay, this is another inverter, 7404, and it goes from there into a 7411 and another 7411. This is 3-input AND gate, and then it goes into a 7420 LS27, which is a 3-input OR gate. Now on this side you can see a whole bunch of transistors, okay, and the LEDs, and on this side you can see a whole bunch of transistors and LEDs. So what this circuit here does is it takes the data coming out of the shift register and it looks for specific sequences depending on what transistor you put in the breadboard here. For NPN, when it shows NPN as it's doing right now, that's this side here, the left side. The output comes out of the 7427 on pin 6 right there, okay, and it feeds right there, and it feeds the driver transistor, which drives all of these, and basically grounds out the necessary segments in the display to show NPN. If the transistor in the socket up here, in the breadboard up here, was PNP, then the signals coming in would be reversed to NPN, and it would drive pin 12, which is right here of the 7427, which goes to this side, which drives these transistors, and it will show PNP. So this is just a NPN PNP driver circuit right here. These LEDs up here are different. They're controlled by another ROM card, which I made right there, okay, which you can see the wires. I don't know if you can just barely see all the wires here coming out of the data lines. And they're basically feeding all these LEDs to show the pin configuration for the transistor, okay? And I'm going to tell you how I did that. So basically, that's all it does. Now for NPN, if that was an NPN transistor, the data that's shifted by the shift register would be two low signals and one high signal for every three clock pulses. Okay, in other words, when it counts 0, 1, 2, those are three clock pulses, and during those three clock pulses, the data, the shift register will output either two highs and one low, or 110, or it'll input 001, or two lows and one high. This circuit will detect that. If it detects two lows and one high, it triggers the NPN side. If it senses two highs and one low, it'll trigger the PNP side. Okay, so that's basically it. And now, the way it distinguishes which pins are which on the transistor under test, right now it's telling me that this transistor, the way I have it, from left to right, as it shows here, is the emitter, the base, and the collector. So let me just speed up this clock real fast so that stays steady. Okay, right there. So now you can see, you can hardly tell that the clock is going because I've got it going so fast, but it's basically going a few hundred hertz right now. So it looks steady, but it's actually still pulsing. But anyways, it's showing that it's an NPN transistor, and the pinouts are emitter, base, collector. Okay. Now the way I did that was, if you take a look at this ROM card, this is a ROM card. Actually, the original ROM card that I made was this one here, which I made a video about. You can check out my channel. And I explained exactly how this thing works. Okay, but as you can see, it's had its day, so I kind of redid everything. Anyways, I put that aside for now. And then I originally had built this one here, which I put with pins that I can basically just stick on the breadboard. But this only, you can see the diodes there on this one here, and then on this side here you can see the transistors and the resistor and the data lines. But I only had three in here, which would only display three different positions for pinout for transistors. So I had to remake it. And so for this original one here that I had, I made this one right now. This one here, take that out. And you can see that basically it's the same thing. It's the same thing as that one there that I showed you, the other one that I showed you, but it's a miniature version of it. Okay, and it has the pinouts, and it has the transistors and resistors on one side. Oops, sorry. Transistors, resistors on one side, and it has diodes on the other side. Okay, I don't know if I think that's out of focus there, but anyways, that basically plugs in to the breadboard right there. So I made it removable so that I could service it and fix it if I had to. Okay, so that goes in there. All right, and what that does is that basically acts like a rotary switch for the transistor under test. The signals from the demultiplexer are coming into the ROM, and then the output is taken by the out of the red lines and feeds the 3-input NOR gate, which is that transistor which drives the shift register, and that all depends on what transistor you put in, and the actual pins, the orientation of the pins that you put into the breadboard. Then the way it distinguishes the pinouts, emitter base collector, is by taking the data out of this ROM. I'm feeding it into this circuit here. This circuit is a comparator circuit. Okay, so here again I have a 7411, which is a 3-input AND gate. And this AND gate, what it does is it takes a signal from each one of the outputs of the hex inverter, because the hex inverter is putting out one high signal to trigger these transistors one at a time. So you need to, and if the light comes on when, for example, pin number 2 is active, because the first signal comes from pin number 1, it gets inverted. So pin number 2 of the hex inverter is active high, that will come into the first line, which will trigger that transistor. So obviously I've got a line on this black wire here, which would be pin number 2. And that high feeds the AND gate. Then I also have a high signal from this LED right here, this wire that feeds another input of the AND gate. And I have a feed from an inverted signal from pin 6 because it's NPN. That signal I'm going across here, I'm using the extra gate in this 7427 as an inverter, and I send that line up this green wire into the third input of the AND gate, so it'll trigger pin number 12 because I'm sending all those 3 signals into pin 1, 2, and 13, which is the first AND gate of the chip. So pin 12 then goes into an AND gate. Okay, this is a 7408 AND gate. And what happens is that's used as one input to the AND gate. The other input comes from the comparators. Now the comparators are wired. I need 6 comparators. I'm using 2 comparators per channel. So what it does is if I get a base signal at pin number 2, if that LED comes on when the number 2 pin is triggered, then what happens is it only activates the first AND gate out of the 7411. So what it does is, even though these comparators are comparing all kinds of configurations of the chip, the other 2 AND gates are disabled. So there's no output from there. It's only the first AND gate that's enabled. That means that any signals that these comparators will detect can only be output at pin number 12. And pin number 12 will drive the first transistor on this card, which is the bottom one, and will drive the appropriate segments of the LEDs to show the correct pin orientation. Okay, and as you can see on this card here, I've got 6 transistors, 1, 2, 3, 4, 5, 6, because there are 6 different positions that you can test a transistor for. And on this side, I've got all the LEDs. Actually, I can pull this card out. I'll show you. This card, I can pull it out and I'll show you here. Okay, so there it is. All right, and this is a little bit more complex than the first one that I showed you. On this side, not really. But anyways, here are your data lines, data output lines, and here are your address lines right here, which will activate each transistor. And then as it does so, it will activate each line going across, and then turn these data lines into low and high signals as required to turn on the LEDs appropriately. Okay, so that's basically how this works. So I can put this back in, and the LED should start working again. There you go, emitter base collector. So now, so the comparators actually, what they do is there's no reference voltages used on these comparators. The lines just go directly into the transistor. That's it. Because these comparators can detect extremely small, minute voltage differences between the inverting input and the non-inverting input. So what I've done is I've used the base signal. Anytime the circuit detects a base signal, I'm using the main signal that comes out of the 7427 as the base to activate the AND gate high, in order for the comparator to detect the remaining 2 pins on the transistor, whichever 2 pins it needs to detect. So what it does is when it detects that the positive input is higher than the negative input, it will trigger the appropriate output to produce a high at the 7408 and trigger the appropriate output gates. And that will send pulses into the correct lines to activate the transistor that will drive the LEDs accordingly. So, and of course you have 6 of them because you need 2 comparators for each position. So what I'm talking about is, let's say the first pin of the transistor is the base. That means the first 2 comparators will compare the voltages between the center pin and the right pin. If the center pin was the collector and this pin here was the emitter, the collector always has a slightly higher voltage than the emitter. So the comparator will detect that and trigger the appropriate output. Okay, now what I'm going to do is I'm going to show you here, I've got emitter-based collector. If I was to take this transistor out and just reverse it, flip it, it'll show you that trying to get it in the socket here. It'll show you that now it's the collector base emitter, where originally it was, when I flipped this back, originally it was the emitter base collector. Okay, now if I put the base as the first pin, this should show base emitter collector. Or I'm sorry, I moved this in the wrong position here. Okay, that should show base emitter collector. There you go. If I switch the pins again, it should show me the base collector emitter. Okay, and then if I put the base in the middle, in one direction, it'll show me emitter base, collector base emitter. Flip it, and it should show me emitter base collector. And then if I put the base on the right hand side, which is there, that will show me the emitter collector base. And if I switch the other two pins around, that should show me the, if I can get this, it'll show me the collector emitter base. So you can see that this comparator circuit will detect the correct pins no matter which way you put this transistor in. So there's no need to know where to put the transistor, what pins, and so on and so on. Okay, and also the beauty of this is that it's the comparators. Most comparators, guys, will use reference voltages, and to cause the comparators to detect within a certain window, certain reference window. But I'm not doing that in this case. I'm using the actual positive and negative reference voltages per gate coming directly from the difference of voltages between the collector emitter of the transistor under test, because comparators are sensitive enough to detect those changes, so you can connect them directly. All right, now I'm going to remove this transistor here. I want to show you something else. When you remove it, there's no test switch. It's just everything goes off, all right, because that's like an open circuit. So this was an NPN. I'm going to show you a PNP here. All right, this is a PNP. Now, I've wired all this up for NPN. I originally had it working for PNP, but because I did modifications on it, right now for PNPs, it only shows that this transistor I put in is just a PNP, but I have no display of pinouts because of the fact that I still have to add another 7427 IC right there, and again I have to do a little bit of modifications to this part of the circuit to be able to detect, to trigger the correct segments for PNP for transistors. So I'm still working on that part, and but you can see that this will detect PNP as well, okay, because that's PNP. Now, an open transistor obviously will show that the circuit is like this. You will have that LED coming from the 3-input NOR gate that I built there will be off, that display will be off, and that display will be off, okay? And the counter will keep counting. So that indicates that the transistor is completely open. If one of the pins are open, you will get a weird display. On the display, it will not show emitter base collector. It will show other letters, for example, A, G, or even a full segments, B, or 8. So that indicates that a couple of the pins are either are open on the transistor being tested. Now this one here is a shorted transistor. I know that this one is completely shorted. All the pins are shorted together. I'm going to show you what it does here. When I put it into the socket, you can see that I have absolutely no display. This is off, but this LED is on. Now if I slow the clock down, even though it's counting very slowly right now, you can see that LED does not flash at all, and it should be flashing right now. Because if it was a PNP, I would get at least one low signal for every 3 clock pulses. If it was an NPN, I would get at least one high signal for every 3 clock pulses, but I don't. I get a constant light on with no display. That means that that transistor is dead shorted in all directions. So now I can put back, let me put back the NPN here, and if I put back the NPN with a slower clock pulse, you guys can see exactly what this thing does, okay? Now you can see that, if you can see the clock there, when it starts at 0, and it comes on in position 1. Position 1 means it's the center pin. Okay, 0 is the left pin, 1 is the center, and 2 is the right pin. And you can see that every time it finds the base, the display will come on. This display will show you the emitter base collector. The base is in the middle. Anytime that light comes on for NPN, it's telling you where the base pin is. In this case, it's telling me that it's in the middle, right there, the middle pin. Okay, and of course the light comes on because it's in the middle pin. And that happens in position 1 of the counter. All right. Now you can't see that in fast motion, but in slow motion you can. And basically that's how it works. Now for PNP, I'm gonna put back a PNP here, and to put back a PNP, you will see that the light will actually go off for 3 clock pulses. You see now it's going off on number 2. Number 0 is on, 1 is on, and 2 is off. 0 on, 1 on, 2 is off. So for PNP, you have 2 high signals and 1 low signal for 3 clock pulses. For NPN, you have, let me put this in. For NPN, you would have, 0, high, and low. Low, high, and low. So every 3 clock pulses, you will get 1 high and 2 lows for NPN. And that's basically how this circuit works. So there you go. And every time, of course, the light comes on, it activates the AND gate, and of course the comparator will compare the other 2 pins, and then it sends the result through these other chips into the card, which turns on the display, and it shows you what the pinouts are. All right. So that's my transistor tester right now. This was the original idea that I had when I did the video for this particular ROM. And these ROMs are not hard to build. Okay, this looks like it was quite a job, but I did this very crudely, and I wanted to miniaturize it. I do have very, very miniature components, but surface mount. But I'm not going to do that. I just tried to make it more modular, such as this type. Okay, this type's a lot easier, a lot more compact and accessible. With this type here, I'd have to remove all the wires and stuff like that. This one here, you could just wire the breadboard, and whenever you need it, you just basically pop it into the breadboard. All right, and that's it. But this one here, I made a mistake. I should have added more channels on this one here. So I originally built that, then I realized I made an error, and I had to rebuild it, which I came up with this one here, which has double the amount that one has. And as you can see, it works very well. So when I increase the clock, there you go. There you go. So that's showing me that that transistor is NPN, emitter, base, collector. Okay, guys, so there you go. There's the idea for the transistor tester. Unfortunately, this tester cannot test any other components. It can test some electrolytics with only the light flashing a couple of times. That indicates a good electrolytic. The signals are very low on this since I'm only using 5 volts, and since it's going through a bunch of diodes all over the place, there are diode drops, so the voltage gets pretty close to tri-state mode, which means that it cannot test other components like MOSFETs or VFETs and things like that. It can't test those kind of components yet, but I just wanted to make this video to show the concept of making a transistor tester. This is fully digital. There are no reference voltages whatsoever, even on the comparators. Okay, this is completely working with simple logic, high and lows, one and zeros. That's it, and it's still functional like a regular referenced meter. All right, guys, so yeah, have any questions, feel free to ask. And obviously, I do have a video, like I said, on this. It's called homemade read-only memory. Okay, this is also a read-only memory, and this is a read-only memory, and this is a read-only memory. Okay, these are all made by hand, as you can see. I could easily put this on a microprocessor or a microcontroller, because there are not that many components. It can easily program a memory chip, but I don't want to do that. I want to do it this way because I have full control of every single digit coming out of here, like even mechanically. So, you know, I'd rather do it this way. And this is, to be honest with you, really fun. So, there you go. So, any questions, guys? Feel free to get a hold of me, and I'll be happy to answer whatever you want. I do have schematics on all of this, obviously, because this is quite a bit of wiring here. But I'm not giving the schematics away. Anybody interested in it, I can send you copies, but they are for sale. Okay, not free, they are for sale. So you can get a hold of me through my channel at Cell Electronics. And I guess I'll just leave it at that, and we'll see you guys next time. Thank you.